and Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello dear students. We know that in chemistry different processes are involved and we have studied them also in the past. Can you name some? There are processes, simple physical processes like dissolution, crystallization, catalysis like heterogeneous catalysis, enzyme catalysis. These reactions, do you have any idea where they are occurring? They are occurring at the surfaces. Are you surprised? But it is correct. Let us learn today in this particular unit, surface chemistry, the chemistry of processes or reactions which are taking place at surfaces. So, the name of our unit here is surface chemistry, and what it deals with? Surface chemistry deals with the study of phenomena which occur at surfaces. The first surface phenomenon that we are going to study here is adsorption. Now, what is this adsorption? Adsorption is nothing but the accumulation of molecular species or particles at the surface rather than in the bulk of the surface or solid. This is termed as adsorption. Now, the simple example that we come across in our day-to-day life in school is the teacher comes to the class and writes on the board, and then after some time she rubs it. What happens? The chalk powder falls, isn't it? And after some time you will notice when the teacher goes out of the class that chalk powder has been accumulated on the surface of this table top. Does the chalk powder penetrates into the table? No, but only the chalk particles are getting accumulated on the surface of the table. This is nothing but a simple example of adsorption. So, this is what this definition is telling us about. Now, there are two important terms which are associated with adsorption. The molecular species that are getting adsorbed or settled or accumulated on the surface, they are termed as adsorbate, and the surface or the material on which the adsorption takes place is called as adsorbent. So, the table top, the example that we have taken in the past is an example of adsorbent surface. There are many such adsorbent surfaces such as charcoal, silica gel, alumina gel, clay, colloids. Metals in finely divided state are acting as very good adsorbents. Now, let us take some examples in chemistry of adsorption. Now, let us consider that there is a air chamber, and in this air chamber there are different gases. Now, we want these gases are present, oxygen, hydrogen, carbon monoxide and so on. Now, all these gases are going to create some pressure inside the chamber. Now, if you drop some amount of animal charcoal into the chamber, you will find that the pressure of these gases inside the air chamber decreases. Now, why suddenly the pressure of air chamber decreases? It is because some amount of these gaseous particles are getting adsorbed on the surface of activated charcoal. This is a charcoal particle, and see how the gaseous molecules are coming and settling on the surface of charcoal. So, because of this adsorption, the pressure inside the chamber decreases. We have a methylene blue solution, and that is acting as a dye, and when this methylene blue is dropped over the animal charcoal, this is a glass funnel that you can see, there is an animal charcoal and methylene blue solution is being poured here. So, what is going to happen? Methylene blue particles or molecules are going to get adsorbed on the surface of this charcoal, and what comes out from this funnel is a crystal clear liquid. So, this is another example of adsorption. Silica gel is a very good adsorbent and it adsorbs moisture. Most of our digital apparatus that we buy, camera or CD player, it contains small packets of silica. Have you ever noticed it? So, what is it for? It is just to protect these delicate materials from moisture, because silica is a very good adsorbent and it absorbs moisture. Now, the process of removing adsorbed substance from a surface on which it is adsorbed is called as desorption. Accumulation of particles on the surface is adsorption, and a removal of these particles from the surface is termed as desorption. Aqueous solution of raw sugar, sugarcane juice which is raw in the factories, is usually brown in color, and it is brown due to the presence of organic impurities. Now, we want crystal clear sugarcane solution. How it is to be made? Pass this raw sugarcane juice over the bed of animal charcoal, and you will find that these organic impurities are getting adsorbed on the surface of charcoal, giving us crystal clear liquid of sugarcane juice. This is the difference between the adsorption and absorption. This clearly indicates how the absorption is different from adsorption. See, in adsorption what is happening? The particles are just getting settled on the surface in both these types, okay. But in absorption what is happening? The particles are not only getting adsorbed, but they are slowly penetrating into the bulk of the surface. So, that is the major difference between adsorption and absorption. So, now after this slide we are going to show one small activity which is going to give us clear cut idea about adsorption and absorption. Students, here we are going to see a small activity in which we are going to see the difference between adsorption and absorption. Here I have an indicator which is methylene blue, and this I am going to add into this beaker. And I have a piece of chalk over here, okay, and now I am going to dip this chalk in this methylene blue solution from both the sides, so that it becomes completely blue. Can you see here, the chalk has become completely blue from all the sides, right? Now what I will do is, the activity is quite simple. I will break this chalk. Now if you see, what part I am showing is the bulk, this white color portion of this chalk piece is called as bulk of the chalk or bulk of the solid, and the outer portion has become blue. So why only the outer portion has become blue, and why not the inner portion or the bulk has become blue? Now here we can explain what is adsorption and what is absorption. The outer surface of the chalk has become blue because the methylene blue molecules have adsorbed on the surface of the chalk. They are not getting absorbed in the bulk of the chalk. If they had to absorb in the chalk, then the inner portion or the bulk also would have become blue. Since they are not going or they are not penetrating inside, we can say that here absorption does not take place, only adsorption takes place. So here this is a small activity, in fact, just to see what is the difference between adsorption and absorption. Sometimes adsorption and absorption can take place simultaneously, both occurring together. When such a process occurs, it is called as sorption. Now we will see why at all this adsorption takes place. Now consider that this is a surface. This surface has molecules at two different places. Molecule is present on the surface and molecule is present in the bulk. Let us consider one molecule is present here on the surface. I am just considering one out of many. And here there is one molecule which is present in the bulk. Now the molecule which is present in the bulk is surrounded by similar molecules from all the sides. So this molecule experiences forces of interaction from all the sides by similar kinds of molecules. So, we say that this particular molecule is a balanced molecule which is present in the bulk, whereas this molecule which is present over here, it is surrounded by similar type of molecules only from here, this side. On the top, such molecules are not present. So, forces of interaction are only from downside, not from the top. So, this molecule here is unbalanced and it is experiencing residual forces from down. This residual forces it will try to reduce. And how it will try to reduce? By attracting the molecules on its surface. And therefore, molecules get attracted and accumulated on the surface in case of adsorption. So, this is the mechanism of adsorption. We have just now seen the mechanism of adsorption, and since in adsorption the residual forces are getting reduced, the surface energy also gets reduced, and since the surface energy gets reduced, delta G becomes negative. That means adsorption is an exothermic process. When the gas is adsorbed, what is happening to the freedom of particles? Freedom of particles is also reduced, and therefore entropy value decreases. Delta S becomes negative, and since delta H is negative and delta S is negative, delta G, that is Gibbs free energy change, also is negative. That means adsorption is a spontaneous process. We will see now what are the different types of adsorptions. There are two types of adsorptions, physical adsorption and chemical adsorption. Now, when do we say that an adsorption is physical? When the forces of interaction between the adsorbate and the adsorbent molecules are weak van der Waals forces of interaction, we say that it is physisorption or physical adsorption. In case of chemical adsorption, the forces of interaction between the adsorbent and the adsorbate molecules are chemical bonds, and preferentially they are covalent bonds. Chemical adsorption is also called as chemisorption, and physical adsorption is also called as physisorption. In this particular slide, we are going to see what are the comparison points between the physisorption and chemisorption. One thing we have already discussed, that is the forces of interaction between the dispersed phase and the forces of interaction between the adsorbate and the adsorbent molecules. Physisorption is not specific in nature, whereas chemisorption is highly specific in nature. Physisorption is reversible, whereas chemisorption is irreversible, because in chemisorption chemical bonds are involved. Once chemisorption takes place, it cannot be reversed back. Physisorption depends on the nature of the gas, as well as chemisorption also depends on the nature of the gas. In physisorption, more liquefiable gas are readily adsorbed, whereas in chemisorption the more reactive substances or gases are readily adsorbed. In case of physisorption, enthalpy of adsorption is very low, between 20 to 40 kilojoules per mole, whereas in case of chemisorption, the enthalpy of adsorption is very high, that is between 80 to 240 kilojoules per mole. Physisorption is favored at lower temperature. At higher temperature, physisorption is likely to get converted into chemisorption, whereas chemisorption is favored at higher temperature. Physisorption does not require any appreciable amount of activation energy, whereas in case of chemisorption, high activation energy is necessary. Both physisorption as well as chemisorption depends upon the surface area of the adsorbent. Larger the surface area, greater is the extent of adsorption. Physisorption leads to formation of multimolecular layers, whereas chemisorption only forms unimolecular layer. We shall see how it is. You see in this particular picture, in physisorption, one layer, upon that another layer can be adsorbed, upon that another layer can be adsorbed. So, this is multimolecular layer formation, This is possible because here physical forces of interactions are involved. In this case, that is chemisorption, only one layer of molecules can get accumulated on the surface because chemical bond formation is taking place between the adsorbent surface and the adsorbate molecules. Okay, so second layer cannot do that because first layer is already present on the adsorbent. So this is the types of adsorption that we have just now seen. Physical adsorption, just see there is no formation of a chemical bond over here, whereas in case of chemical adsorption there is actually a chemical bond which is established between the adsorbent surface and the adsorbate molecules. Now we are going to study a very important part of this adsorption, and that is called as adsorption isotherms. Adsorption isotherms gives us the relationship between the variation of the extent of adsorption with pressure at constant temperature. It also gives us the relationship between the extent of adsorption with pressure at constant temperature. That is called as adsorption isotherm. Since the word isotherm is involved, we have to maintain the constant temperature. Under adsorption isotherm, we have to remember Freundlich adsorption isotherm. Freundlich adsorption isotherms give us the empirical relationship between the extent of adsorption and the pressure for physical adsorption of gases at constant temperature. So this x by m actually is directly proportional to P. That means for physical gaseous adsorption, the extent of adsorption x by m is directly proportional to P raised to 1 by n. Now if you remove the proportionality sign and put the equality sign, you will have to introduce the constant of proportionality k. So in this particular relationship, we have two constants k and n, and both these constants are depending upon the nature of the adsorbate molecule at a given temperature as well as on the nature of the adsorbent. Now what is this x? Here x stands for the mass of the gas which is adsorbed and m stands for the mass of the adsorbent surface. So that x upon m is the mass of the gas which is adsorbed per unit mass of the adsorbent. So owing to the relationship Freundlich adsorption isotherm, if we plot x by m against P, we are going to get this particular graph at 3 different temperatures. So this is plotted at lower temperature, this is slightly higher temperature, this is still higher temperature. So what is happening? At the beginning the extent of adsorption increases and then it almost remains constant. This is how is the nature of the graph for each temperature. Another important observation which we can make here is physical adsorption decreases with increase in temperature. See, T3 is the highest temperature over here, and see at T3 only there are lower values of extent of adsorption compared to T1 and T2 which are slightly lower values of temperature. So we can say that physical adsorption for gases on the adsorbent surface is favored at lower temperature. So the same relationship we are continuing with x by m is equal to k into P raised to 1 by n. If you want to take logs on both the sides, then the relationship becomes log of x by m is equal to log of k plus 1 by n log of P. Now this 1 by n can have two values, okay, and based on that we can find a relationship whether the extent of adsorption is dependent on pressure of the gas or it is independent on the pressure of the gas. So here we will see x by m is equal to k into P raised to 1 by n. 1 by n can have values from 0 to 1. So we will take the values of two extremes. If 1 by n is equal to 0, and if you substitute it in this equation, then we will have to substitute it as P raised to 0. P raised to 0 is 1, therefore x by m will be equal to k. It means that extent of adsorption is independent of the pressure of the gas. On the other hand, if we take 1 by n is equal to 1, then x by m will be equal to k into P raised to 1, right. That means here extent of adsorption will be directly proportional to the pressure of the gas. So, like this we can find out based on the values of 1 by n whether the extent of adsorption is independent of pressure or it is dependent of pressure. So, the earlier relationship applying logs to the Freundlich adsorption isotherm, we are getting the equation of the type y is equal to mx plus c. If you plot log of x by m against log of p, we are getting the straight line which can be extrapolated on the y axis to get an intercept, and this intercept is nothing but log of k. So, from this graph we can find out what is the value of n or what is the value of 1 by n and what is the value of k for a given adsorption at a given temperature. We have just now seen the adsorption of gases on the surface. Is it possible to adsorb the solute from solution? Yes, it is possible. Here we have taken adsorptions from solution phase topic. Now suppose we are having a solution of acetic acid with a particular concentration, say suppose 1 molar, and in this acetic acid solution we are dropping some amount of animal charcoal. Now after some time if you try to find out what is the concentration of acetic acid, you will find that it is definitely less than 1 molar. Now why it has to become less? It is because some amount of acetic acid has now accumulated on the surface of animal charcoal. This is nothing but adsorption of solute from the solution phase. The second example that we can cite here is the magnesium reagent, which is blue in color, and magnesium hydroxide, which is a precipitate, is white in color. If you drop magnesium hydroxide white precipitate into magnesium reagent, you will find that after some time white precipitate has become blue. Now why is it so? It is because the adsorption of magnesium reagent particles on the surface of magnesium hydroxide. So this indicates that there is a possibility of adsorption of solute from the solution phase also. So this is a modified Freundlich equation for the adsorption from the solution phase. This is x by m, that is extent of adsorption, is equal to k into c raised to 1 by n. Now this is the only modification which we have to make here, because in case of solution the most important measurable property is concentration or molar concentration, not the pressure. So remaining everything is same, even the temperature dependency remains same. If you increase the temperature, you will find that the adsorption from the solution phase decreases. With the increase in the surface area of the adsorbent, you will find that the extent of adsorption of solute on the surface of the adsorbent is also going to increase. Applications of adsorptions: production of high vacuum. Suppose there is an air chamber and we want to evacuate that particular air chamber. What do? We apply suction, isn't it? But with the suction also you cannot make the chamber 100% air free. To remove the traces of air, one has to drop a suitable adsorbent like animal charcoal. Traces of air will get adsorbed on the surface of the charcoal. Gas mask. Gas mask which are used by miners in the coal mines, they will have to face very poisonous gases like carbon monoxide and carbon dioxide. So gas mask surfaces are usually made up of animal charcoal. These animal charcoal surfaces can adsorb poisonous gases like carbon monoxide and carbon dioxide on their surface. The third thing is control of humidity. We have just now seen silica gel example which can adsorb moisture from air. Heterogeneous catalysis, catalytic reductions we have seen in the past, in which the reactants are getting adsorbed first on the surface of the catalyst. Removing color matter from the solution, example is raw solution of sugar cane, which we have to pass through the animal charcoal bed in order to adsorb the organic impurities. Curing diseases. The medicines or drugs that we take to kill the germs, actually what they do, these medicine molecules or drug molecules, they are going to adsorb first on the surface of the germs and then will show its inhibiting activity. Froth flotation process, we are making use of pine oil as a collector. These pine oil particles are going to adsorb on the surface of the mineral particles. Adsorption indicators, basically silver iodide is used as a very good adsorbent indicators in titrations. Chromatographic analysis also, you will find that the substances are getting adsorbed at different points on the adsorbent surfaces. So, these are some of the applications of adsorption from day to day life. We are going to study now catalysis, which is another surface phenomenon. What is catalysis, all of you? Naturally, it is a reaction or a process which involves a catalyst. Then what is a catalyst? A catalyst is a substance which alters the rate of the reaction without itself undergoing any change in the concentration and composition. That is what we have learnt in the past. So, let us see some example. Potassium chlorate here is decomposed to potassium chloride and oxygen. Usually this reaction occurs at a very high temperature, but if you use manganese dioxide as a catalyst, you will find that the rate of the reaction is accelerated and also this reaction is taking place at a lower temperature. So, as per our earlier discussion, what is the definition of catalyst? Substances which alter the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalyst. And the phenomenon which involves the use of catalyst is called as catalysis. Promoters and poisons are the two terms which are very often associated with catalyst. What are promoters? Promoters are the substances which enhance the activity of the catalyst. They enhance the activity of the catalyst, whereas poisons decrease the activity of the catalyst. We have learned Haber's process for the manufacture of ammonia. There we are using iron as a catalyst and molybdenum is used as a promoter of iron. In case of poisons, we can take an example of Rosenmund reduction in which acid chlorides or acyl chlorides is converted into aldehyde. Now, if you want the reaction to stop at aldehydic stage and if you want to prevent the further reduction, then we will have to add poison quinoline to the catalyst palladium over barium sulfate. There are two types of catalysis, homogeneous catalysis and heterogeneous catalysis. What is homogeneous catalysis? When the reactants and catalyst are in the same phase, the process is known as homogeneous catalysis. You see here in the example, both the reactant sulfur dioxide and oxygen are gases. Catalyst is also in the gaseous phase. So, this is homogeneous catalysis. In the second example, both are in the liquid state, methyl acetate as well as water, and here even the catalyst H plus ion is in liquid phase. Catalyst and reactants are in the same phase and therefore, both these reactions are the examples of homogeneous catalysis. In heterogeneous catalysis, the reactants and catalysts are in the different physical phase. If you see the example, sulfur dioxide and oxygen both are in the gaseous phase, but platinum is in the solid phase. In this case, nitrogen and hydrogen are in the gaseous phase, but iron, which is used as a catalyst, is in the solid phase. Phases are different, therefore, they are the examples of heterogeneous catalysis. Let us look at the mechanism of heterogeneous catalysis. It involves 5 steps. First one is, see, these are the reactants A and B. These reactants first should diffuse towards the catalytic surface. These are the catalytic surfaces, empty spaces here are the free valence. Now, first reactant A and B will come towards the surface, that is diffusion. Then they are going to get adsorbed on the surface. This is adsorption, all of you. B is adsorbing on the surface, A is adsorbing on the surface. So, this is the second step, adsorption. Once they are adsorbed and settled on the surface of catalyst, bond formation will take place between A and B. Bond formation will take place between A and B, that means reaction is taking place, and once the reaction is taking place, product will be formed and that product will get desorption. It is going to get desorbed, removed from the surface. AB is our product, and once the AB is dissolved from the surface, it is going to get diffused from the surface of the catalyst. So, this is mechanism of adsorption. Shape selective catalyst is another interesting topic of catalysis over here. Here, the pore structure of the catalyst and size and structure of the reactant and product molecules decide whether the reaction is going to occur or not. The catalytic reaction that depends upon the pore structure of the catalyst and size of the reactants and product molecules is called as shape selective catalysis. Zeolites are very good examples of shape selective catalyst. They have honeycomb like structures. Now, what are these zeolites? In zeolites, there is something called as ALOSI 3-dimensional framework, which is called as aluminosilicate framework. Actually, it is a silicate framework, but in that framework, when some of the silicon atoms are replaced by aluminum atom, you are going to get something like this ALOSI framework. This is the structure of zeolite. They are porous, okay, and how this porous structure is, see what is the structure of pores of zeolites is shown over here, and this is how actually solid zeolite looks like. Okay. Now, one of the important application of zeolites is in petroleum industry. Last year we have learnt about ZSM-5 zeolite, isn't it? What was it used for? We have studied that it is used for conversion of alcohol directly into gasoline. So, that is very important zeolite ZSM-5. Now, we are going towards enzyme catalysis. Now, what are enzymes? We have learnt that enzymes are complex nitrogenous compounds. They are actually proteins and they are forming colloidal solutions in water which are quite stable. They are also called as biochemical catalysts and they are very highly efficient. They are working mostly in all the plants and animal cells as catalyst. Therefore, these enzymes are also called as biochemical catalyst, and the phenomenon which involves enzymes as a catalyst is called as biochemical catalysis or enzyme catalysis. These are some of the examples of enzyme catalyzed reactions. First one is inversion of cane sugar. You have to remember these enzymes, okay, along with the reaction which they catalyze. This is inversion of cane sugar. Cane sugar is converted into glucose and fructose by the enzyme invertase. Now, this glucose is converted into ethyl alcohol and carbon dioxide. The reaction is catalyzed by the enzyme zymase. Conversion of starch into maltose. This is starch which is converted into maltose, a disaccharide, okay, and this is the hydrolysis reaction actually which is catalyzed by the enzyme diastase. Conversion of maltose into glucose is converted or is catalyzed by the reaction enzyme which is called as maltase. There is an enzyme which is called as urease which is catalyzing hydrolysis of urea into ammonia and carbon dioxide. So, these are the various examples of enzyme catalyzed biochemical reactions. Now, this enzyme catalysis is characterized by certain properties. What are the properties or special features which are associated with enzyme catalysis? First one is they are highly efficient. One molecule of enzyme can catalyze 1 million substrate or reactant molecules. Such is the efficiency of enzyme catalyzed reactions. They are highly specific in nature. One enzyme can catalyze only one particular biochemical process. One enzyme cannot be used for 2 or 3 different reactions. They are highly active under optimum temperature. Now optimum temperature is the temperature at which the enzyme is going to show its highest activity, and this temperature range is always between 298 to 310 Kelvin, and our body temperature is also 310 Kelvin. So our body temperature is suitable for enzymes optimum activity. Highly active under optimum pH. Now what is this optimum pH? Of course it is the pH value at which the enzyme shows its maximum activity. So the optimum pH value here is between 5 to 7. Next one is enzymes show increased activity in the presence of activators and coenzymes. Now what are these activators and coenzymes? Coenzymes are nothing but vitamins which are non-protein part. Okay. These vitamins are enhancing the activity of enzyme. At the same time, we have something called as activators, which are nothing but metal ions like sodium ions, manganese ion, copper ions, which are weakly bonded to the enzymes and they enhance the activity of the enzyme. Enzyme amylase in the presence of sodium chloride is very active. So here sodium ions are acting as activators for enzyme amylase. Like catalysts, here enzymes are also affected by what are called as inhibitors and poisons. Poisons inhibit the activity of the enzymes. Okay. Many drugs are acting by this principle of inhibiting the enzyme action. This is the indication of the mechanism of enzyme substrate complex, how the enzymes are catalyzing the reaction. Okay, that particular mechanism is shown in this particular slide. There is a proper lock and key mechanism or lock and key hypothesis which explains the formation of product by enzyme catalyzed reaction. See, you have an enzyme here. That enzyme has got an active site, and that active site of the enzyme can easily fit into the shape of the substrate. So there is a proper key for a proper lock, so lock and key hypothesis. So this active site of the enzyme has got various functional groups on it. So once it fits into the substrate, it forms what is called as enzyme substrate complex, wherein the reaction takes place and the products are formed. And these are the two products. Once the products are formed, they are getting detached from the enzyme, and we are going to get the enzyme back as it is without any change in its concentration and composition. So this is what we have to study about the mechanism of enzyme catalyzed reaction.
Prudent Scholars, powered by Lupin Pharmaceuticals.